Today we're going to learn more about logarithms. Before we get into logarithms, let's review a few things that we need to know. First, there is that very simple exponential rule that says a to the n times a to the m is the same as a to the power of n plus m. If the base is common, we can add the exponents. Second, let us just quickly recall the definition of a logarithm. So we introduced the idea of logarithm using log 2 of 8. Log 2 of 8 is 3 because 2 to the third power is 8. In general, log a of b is c means that the base of the logarithm is the base of the exponential. Log a of b is the number of a factors we need to multiply with each other to achieve the product that is b. So in other words, a to the c equals to b. We're going to come back to this, but also both a and b need to be positive so that log a of b is defined. In addition, a cannot be 1. So this was the definition, and the definition had two consequences. We have two properties so far. The first one is pretty straightforward. Just a few examples for that. What would be log 2 of 8? Well, we just reviewed that. Log 2 of 8 is 3 because 2 to the third power is 8. We need 3 2's to get to 8. How about log 2 of 64? So the question is, how many 2's do we need to multiply so that we achieve the product 64? Well, 64 is 2 to the 6th power, so we need 6 2 factors to achieve that product. How about this one? Log 2 of 2 to the 100th power. So the question is, how many 2 factors do we need so that if we multiply them all together, we achieve the product that is 2 to the 100th power? And the answer is, well, how about 100? And that's basically the first rule of logarithm. So log a of a to the power of b is just that power b. To achieve a to the b as a product, we are going to need exactly b many factors a. So this second rule is a little bit trickier. What would be 2 to the power of log 2 of 8? Well, that's not difficult because we know what log 2 of 8 is. That's 2 to the third power. That's 8. Let's see another one. 3 to the log 3 of 9. Well, log 3 of 9 is the number of 3 factors we need for the product 9. That's 2. So we have 3 squared, which is 9. So notice that there is some sort of a cancellation going on that we're always just going to get back the original number. So the question is, would 2 to the log 2 of 7 be 7? Would a to the log a of b be the same as b? Well, let's check it out. If we call log a of b x, then that means that x is the exponent, the number of a factors that we need to achieve the product b. So that means that a to the x power will give us b. And now comes the magic. X is log a of b. So a to the log a of b must be then b, which is that second property we're looking at here. A to the log a of b is just b again. That might sound strange at first, or look strange at first, but what is log a of b? It is the exponent that if we put on the top of a, we're going to get b. So if we do that, we will get that b. So it's sort of a promise fulfilled. All right. The third ingredient is the fact that exponential functions are one-to-one. If the base is greater than 1, we have exponential growth. If the base is less than 1, then we have exponential decay. But in either case, the function is one-to-one. That means that if x1 and x2 are different, then a to the x1 and a to the x2 must also be different. So that means that every x sort of has their own y. No y value is taken twice. For a function to be one-to-one is a very useful property. In our particular case, here is what it gives us. We can say that if 2 to the a equals to 2 to the b, then a must be equal to b. That's what a one-to-one function does. So if 2 to the a equals to 2 to the b, recall that f of x equals 2 to the x is one-to-one. Which means, well, there are two ways of looking at it, really the same, that if a and b are different, then 2 to the a and 2 to the b also must be different. Or in other words, if two powers are equal to each other, then we can conclude with certainty that the exponents themselves must be the same. So this step is what we're going to use today. That is not always the case. For example, a squared equals b squared does not imply at all that a equals b, or a equals negative b, right? Now the reason that this here worked and with the squaring function it didn't, because the squaring function is not one-to-one. So you can have two different things, namely opposites, like -2 and 2, that will land on the same y value. So we don't have this nice, useful property. And so we have to be very, very careful when we are trying to take the square root of both sides of an equation, so to speak. This is not the case with the exponentials. Exponentials have this nice property. Okay, so we're ready to prove the main theorem.